Good morning. Now we're going to move on to hypothesis tests for two different qualitative variables and discuss how to find association between two different qualitative variables. Again, I emphasize this is a hypothesis test between qualitative variables. Okay. So far we've been doing hypothesis tests between quantitative variables, so we could compute the mean and standard deviations and proportions and do hypothesis tests on them. Now this test is between categorical or qualitative variables. And it tests for association. Good thing is we're going to use the chi-squared distribution, so you don't have to learn a new distribution. Okay, and we're going to do a chi-squared test for it. And we're going to learn how to do that through two-way tables that are set up from two different factors. Okay, so if you remember, for ANOVA we called it one-way ANOVA. That was for one factor. We only did one factor, multiple levels, right? Here we're going to do two-way tables, so two factors that may have multiple levels underneath each, but the variables are categorical. Okay, so we're going to describe relationships between two-way tables and then set up a hypothesis where it says there is no association between the two variables, and alternate is that there is. I'm going to perform a hypothesis test using expected values and seeing if there's a difference from those expected values. So for example, the way you want to think of a two-way table is that there are two different variables that you're interested in. Okay, so two factors. That's why two-way. And they're two different categorical variables. Let's say, for example, you have age group. Now, age is a numeric variable, but you put it into intervals, so therefore it became category. So 25 to 34 is a category, and 35 to 54 is a category, and so on. Okay, so this is a categorical variable, age group, and a categorical variable, education. You're trying to see if education is associated with what age group a human being belongs to. Okay, so you organize the data. Okay, you have to organize the data in a two-way table. And then there's going to be a row variable. Okay, in this case, the row variable is education. That has 1, 2, 3, 4 levels. Notice these are, again, categorical variables. Okay, it's not numeric. And you have a column variable, which is age group. So row variable was education. Column variable is age group. And you have 3 levels for column variable. Okay, and each value is called a cell. Okay, the intersection of the two values. That means there's 4,459 students or people that are in the age group of 25 to 34 that did not complete high school. Okay, so you see the cell values are frequencies. Okay, so the cell values are frequencies. Now, when we look at just the individual totals, right, if you sum them up and you get the totals, if you look at just the individual totals of, let's say, all high school, that is called a conditional distribution. Okay, we're just looking at the totals, not paying attention to the age groups, then that distribution is called conditional distribution for high school. Or if you're looking at the totals for age and not paying attention to the education level, that's the conditional distribution for age. Okay, so we want to test using those distributions if what we observed is very different than what we expect. Okay, suppose you have 171 students and you observed there to be around 87 freshmen, around 30 something sophomore, 20 something junior, and about 20-ish senior. Okay, now when you don't have any data set, what would you expect? Equal numbers throughout, right? If you have 171 students, you would divide it by 4 and expect around equal numbers throughout. But what you observed is different from what you expect. So the question is, if what you observed is very different than what you expect, then there is a relationship between the two different categories. Okay, so we do this by comparing the actual counts, which is the observed counts, observed values, with the expected counts. Okay, where we say H naught is that the row variable and column variable are not associated okay, and H1 is that the row variable and column variable are associated. Remember, H naught is the null hypothesis, where you're not picking any sides, right? If you're not picking any sides and you don't have any information, then you're going to think they're not associated, they're independent of each other. But if you want to pick a side, well, then you're going to think they are dependent on each other, so they are associated. Okay, so we do this by computing the expected count for each cell. We're going to compute an expected count for each cell, and that's going to be the row total multiplied by the column total divided by sample size, which is the total. That's what I like to call it. It's easier to remember. The total of all the totals. Okay? And then we can find the difference between what you observed and what you expected, square it, divide it by what you expected, and sum it up over all the cells. Okay? And if you have a large chi-squared value, well, then you're probably going to get a small p-value, and so you're going to reject a null hypothesis. If you get a small chi-squared and you get a large p-value, you're probably going to fail to reject null hypothesis. Okay? And that depends on degrees of freedom. And the degrees of freedom for the chi-squared, critical or statistic, for two-way tables, is the number of rows minus 1 multiplied by number of columns minus 1. Okay, number of rows minus 1 multiplied by number of columns minus 1. So for that education example, right, education versus age group, right, there was 4 education levels and 3 age groups. So degrees of freedom would be 4 minus 1 multiplied by 3 minus 1. Okay, so 3 times 2, 6. All right. And then find out the p-value and make your conclusion. Okay. Now the assumption for the chi-squared test for two-way tables that you have to pay attention to is that they have to be randomly sampled. That's fine, we're going to assume random all the way through. But the big thing is you have to expect each of the cells to have at least 5 values. Okay, so expected values in each cell should be at least 5. In fact, Minitab is going to give you a warning if this doesn't hold. All right. Now, when you're trying to do these tests, you might think, if I have just a 2 by 2 table, right, something that looks like male, female, let's say left-handed or right-handed, right? And you have some values there and some values there, right? And you want to see if there's a difference between them. Are they independent of each other? Well, why don't I just do a proportions test, 2 proportions, right? The number of left-handed students that are male out of the total number, right? Compare that with the number of left-handed females out of the total number for females, and see if there's a difference between them. And in fact, your chi-squared value is going to be the same as the z-squared value. If you get the z-stat and then square it, that's going to be the same as the chi-squared if you have exactly a 2 by 2 table. But the chi-squared test for association is more generic. It holds for even more than 2 different levels, right? You can do 3 or 4 or as many as you like. If you go above 4 levels, your data can look a little more congested. Okay, so stick to at least stick to anywhere above 2 to less than 5 levels to get clean results. All right, so let's look at an example. Franchise businesses are sometimes given exclusive territory by contract. This means that new outlet will not have to compete with other outlets of the same chain within its own territory. How does the presence of an exclusive territory clause in the contract relate to the survival of a business? You take 170 samples, okay? So n equals to 170. And you see whether the firm was successful or not, right? These are categorical variables. Success, yes or no. And if the firm had exclusive contract or no. Okay, so exclusive contract, yes, no, and success, yes or no. It's a 2 by 2 table. Okay. Degrees of freedom is 2 minus 1 times 2 minus 1, which is 1. Right, we can look at the data just by making a bar plot and see, yeah, you expect them to be a difference, because just looking at the success, there's a significant difference between yes and no contract holders. So you set up your hypothesis that there is no relationship between exclusive clause and success, and alternate that there is a relationship between the 2 variables. Okay, and you can either do it by hand by computing the differences, or you plug it into Minitab and you get the output. So let's practice that in Minitab. All right, then we take this data set of 108, 15, 34, and 13, this table, and we put it into Minitab. Okay, and once it's in Minitab, See, I've given the headings exclusive yes, exclusive no, success yes, no. We go to stat, down to tables, chi-squared test for association. Now we're never going to use the raw data option. We're going to have it summarized in two-way tables because I want you to practice getting it to this format, right? It's all summarized in a table for you. It's a two-way table. And you put in the two different columns, exclusive yes and exclusive no. Minitab can take care of the rows for you. Okay, so you put in two different columns. Now click on statistic, and you want to check off each cell's contribution to chi-squared down here. Then click OK, and click OK. Okay, you get the following output. What we're going to use is the Pearson's chi-squared value. That's your chi-squared stat. Okay, that's the method we learned, 5.911. Degrees of freedom is 1, and p-value is 0.015. Okay. The middle values, so first value is the observed value. Minitab tells you what they are. Count means the observed counts. The middle parts are the expected counts, the expected value that we can compute using the formula. And then the third one is your contribution to chi-squared. That is the gap between your observed minus the expected squared divided by the expected. Okay, that's that formula. Okay, so based on that output, the p-value is 0.015. Okay. And at a 5% alpha, we can reject null hypothesis. Therefore, we found that there is a relationship between exclusive territory and the success of a firm. Right? And also we can state the chi-squared stat from this value. That is exactly 5.911. Excuse me. 5.911. Okay. Degrees of freedom is 1, right? Number of rows minus 1 times number of column minus 1. All right. So that's how you do it in Minitab and interpret the results. Fairly straightforward. Let's try to do one in hand. We're trying to see if the relationship of readership is affected by imagery. Okay, readership that's affected by imagery. If the imagery is sports related or non-sports related, will the readership of men or women or just general be affected? That's the question. And you want to test it at alpha of 5%. Now I've given you the observed values. You can in fact type this into Minitab and go from there, but we should practice doing it by hand because there may be a question to fill in this table. So the degrees of freedom in this case is what? Number of columns, which is 3 minus 1, 2, times number of row minus 1, so 2 minus 1. So 2 times 1 is 2. So at least we know the degrees of freedom is 2. Okay. Now expected value we said is row total times column total divided by total sample size. Okay, so let's find out the totals first. So first, we know it's the total for not sports is 248 plus 514 plus 351. Okay, that total is 1, 2, 1, 3. Okay, and then for sports it's 66 plus 105 plus 225. And that is 396. If we add that to 1213, we get the total, which is 1609. Okay, and now we can also add across the rows. So 248 plus 66 gives us the total for general readership. And that would be 314. And the total across men's is 514 plus 105, 619. Okay, and 351 plus 225 is 576. And if you add those up, you'll see that we get the same value for the total. Okay, so to find the expected value, here we do row total. So for that corresponding row, it's 1213 times column total, so 314, divided by total, 1609. Okay, so 1213 times 314 divided by 1609 is our expected value. So this turns out to be 236.7. Okay, now let's do it for the men's. The row total stays the same, so 1213 times, but now the column total changes to 619 divided by 1609. That gives you 466.7. And then let's do one more for women. That would be 1213 times 576 divided by 1609. That becomes 434.2. All right, and then now find this intermediary value. Okay, so 248 minus 236.7, square that number, divided by 236.7. That is 0.54. Let's practice one more. We have the observed value, which is 514, minus the expected value, 466.7, square that difference, divided by the expected value, 466.7. That is 4.79. One more, the females. So the observed value, 351, minus the expected value, 434.2, square that difference, divided by the expected value, 434.2. Okay, so 15.9. Can you do the same for the bottom row? Once you find all these intermediary values, okay, you don't really need to fill out the total, these values. Okay, you can keep them empty. Once you fill out these values, then sum up these three numbers and these three numbers to find the chi-squared statistic. Okay, so let's see how that looks like. When we look at a plot between them, you would expect there to be some relationship. You notice how not sports for men's is much higher, sports is smaller, and so on, and it changes a little bit across the three different groups, right? So when we compute the values, right, you see that it eventually we compute the totals, and once we fill it all the way out, we get a chi-squared value of 80.87. Okay, again, these expected values is row total times column total divided by sample size. Okay, and this chi-squared value is the summation of these 6 numbers. Okay, so summation of over the cells of the observed minus the expected squared divided by the expected. That gives you the chi-squared value. What's the degrees of freedom? 2. And the p-value, if you look it up on Minitab, you can put in the chi-squared value of 80.87, degrees of freedom of 2. Remember that chi-squared distribution is one-sided, right? Put in a chi-squared value of 80.87, and that area will be the p-value. Okay. You can use the table also if you like, or else Minitab is much quicker, and you got yourself the p-value of about 0. 2.7 times 10 to the negative 18, so 0. Therefore, rejected null hypothesis, there is a strong association between sports and readership. Sports imagery and readership. And again, we can run this through Minitab. You just type in this information in Minitab, and Minitab gives you this output. Notice here I didn't print out that third cell value, which is the observed minus the expected squared divided by the expected. You can choose to do so, or you cannot. It's up to you. But if there's a table that requires you to fill out that intermediary value, you should, if you're using Minitab, you should print that out. You should let Minitab compute those, unless you have to hand calculate them and then put them in there. Okay? And so you get the same conclusion. All right, this brings an end to this chapter. Again, make sure you're following along with the homeworks and the quizzes, and make sure you're keeping in tabs with the deadlines of each of those assignments. Contact me if you have any questions, aroy@bgsu.edu.